to talk about learning target 6C, which is all about the power rule for derivatives. So in our last section, we learned about the definition of the derivative, which is the limit of that difference quotient, and we went through what is kind of a long and tedious process of getting the derivatives. Now we can always do that using the definition. That's what the definition is there for and gives us. But you might have noticed that there's some patterns that exist as we started to use that definition over and over again on some similar types of problems. And in this section, we're going to start to talk about some of those patterns that we see. One thing I want us to think about and always keep in the back of our head is what the derivative actually is. So the derivative is the slope of the tangent line. And we talked about this idea up here that I have on our little recall in our last video and how we constructed the definition itself. But that derivative again is the slope of the tangent line. Our first rule that I'm going to have us talk about is the derivative of constant functions. So if c is a constant value, I can take the derivative of c and I'm always going to get the same answer out of that. And the reason this happens is because the derivative is the slope of the tangent line. So here I have y equals c drawn on a graph. C is any constant, so I can think about it as whatever my favorite number is. And we know that if we have a graph that's just y equals a number, it produces a horizontal line at that value itself. Now anywhere on this horizontal line, if I were to find the slope of it, my slope would always be 0 because I have no rise and I am just running, if I think back to the rise over run definition of slope from algebra. So what that tells us then, if I take the derivative, so again this d over dx is that operator, that means I want to take the derivative of whatever is in our parentheses, and if I take this derivative with respect to x here of our constant, I am always going to get 0 out because 0 is the slope of our horizontal line, which graphically is representing our constant function, through again the derivative being the slope of the tangent line. Now the second rule we're going to look at is the power rule, and this has to do with when I have x's to powers. So if n is a rational number, so that could be an integer value, it could be a negative number, or it could be a fractional exponent, and we'll see examples of all of those today. Then when I take the derivative, so again d over dx is our derivative operator, when we take the derivative with respect to x of x to the n, I get a pattern that starts to happen. What happens is the exponent comes down, so our n comes down and becomes a coefficient in front. I still have my base of x, but the new exponent now is the original n, where I also subtract 1. And if you look back in your learning target 6b notes, you're going to notice that this happened every single time we did that limit of the difference quotient for a polynomial function. So again, when I take the derivative of x to a power, the exponent comes down and becomes our coefficient in front, and I get x to now the n minus first power. And this will work if n is an integer, if n is negative, or if n is a fractional exponent. The one thing we have to be careful of is x to the n here is in the numerator. Although I don't have a fraction written, this is assumed to be over 1, so I can only apply this power rule if x is in our numerator. If x to the n is in our denominator, we're going to have to use properties of exponents from algebra 1, and as a little kind of side recall here, if I were to have 1 over, let's say, x squared, we could algebraically rewrite this as x to the negative 2 by bringing up that base up to the numerator. Usually in algebra 1, we were doing the opposite, where we were taking x to the negative second and flipping it down to make the exponent positive. But here, in order to use the power rule, if I have a function like 1 over x squared, I'm going to actually have to first rewrite it as x to the negative second before I can use our power rule here for polynomial functions. Okay, our third rule that we have is the constant multiple rule. So if f of x here is a differentiable function of x, meaning that the derivative of f does exist and I can find whatever that derivative is, and if c again is a constant, then I can take the derivative of the product of those two together. So c here is a number, it's a numerical value, it is the coefficient on my function f of x, and if I want to take the derivative of that product, the coefficient here actually plays no effect into my derivative. I like to say that coefficient goes along for the ride of taking the derivative of the function itself, and the derivative of f of x, I don't know what f is, but I can represent that derivative by using, let's say, the prime notation and call it f prime of x, where again f prime of x here is the derivative of f of x. And that coefficient c went along for the ride, and I get c times whatever the derivative of f is. Now, our fourth rules here that we're going to look at are the sum and difference rules. These are very similar, so they get grouped together. Here, if I have two functions, f and g, if they are both differentiable with respect to x, then their sum and difference are also differentiable at every point where f and g have a derivative. What that means is if I have a sum of two functions or a difference of two functions, I can actually term by term differentiate, meaning I can take this operator d over dx and distribute it and get the derivative of f of x plus whatever the derivative of g of x is. Another way that we can think about writing it, and I'll squeeze it down here, is the derivative of f of x using the prime notation would be f prime of x plus the derivative of g of x using that prime notation would be g prime of x as well. Likewise, I can do the same thing with subtraction. I can distribute that derivative over the subtraction and take the derivative first of f of x minus the derivative of g of x. That would be how we'd write it using the operator notation, and then using the prime notation, I could represent the derivative of f as f prime of x, and I could represent the derivative of g as g prime of x. So if I have a sum or difference of two terms that are both differentiable, I can differentiate each one of those term by term. Either get f prime plus g prime if I'm adding them together, or f prime minus g prime if we are subtracting them overall. We're going to go through quite a few examples of differentiating the following functions, and we're going to see that we're going to use at least one of these rules, maybe a few of them in every example. So in our first example here, we have y equals x to the fourth minus x squared plus 10. And what differentiation again means is it means to find the derivative. So I want to find the derivative of y. One way that we could represent that is by calling that dy over dx, and that derivative would be equal to the derivative of each one of these terms on their own. Because I have a sum and difference here of x to the fourth, which we can differentiate, minus x squared, which we can also differentiate, plus our constant of 10. So we're going to term by term differentiate this. Starting with the x to the fourth, I would want to use the power rule here because I have x to a power. So in that power rule, the 4 is going to come down, my base will stay the same to the x, and I'm going to now end up with the 4 minus the first power, which would give me x to the third. Now minus, I can now differentiate the x squared using the same power rule. We have the same idea. Our 2 as our exponent is going to come down to become a coefficient, and now we're going to get x to now the 2 minus first power, which would just give us an exponent of 1. And we know from prior classes that if we don't want to write the exponent of 1, we don't have to, but just to kind of stress there what happened to the exponent by subtracting 1 from it. And then our last term on here, this plus 10, well, plus 10 would be a constant function, and we know from our first rule up here that if I differentiate any constant, whatever that number may be, if there's no variable there, it's just that constant function, so a horizontal line, and the slope of any horizontal line is 0, so I'd ultimately get plus 0. Now, likewise to the exponent of 1, we don't have to write plus 0, but just to emphasize what happened to that one on that example. One question that I've gotten before is, do I always have to write this dy over dx? And the answer to that is yes, because I actually need to identify what is my answer here that I'm finding in my work. If I just put an equal sign here, I'm actually saying that the original function is equal to my derivative. And those two statements are not true. My original function is one function, and the derivative is representing the slope of the tangent line to that function. So I've got to make sure that I'm labeling my work here, so I'm explaining what each piece of these are representing. So I can either use the operator notation, or I'm going to also use the prime notation in some of these examples as well. But I just want to make sure that I'm labeling what I'm finding in each question. Let's look at our second example. So here we have f of x is 3x to the fifth minus 7x cubed plus x. Again, we have a sum and difference of terms here. We want to differentiate f of x, so I want to find the derivative. I'm going to use the prime notation this time. So one way to represent the derivative of f would be to call it f prime of x. So I'm finding my derivative here. Each one of these, again, is going to ultimately use that power rule. So in the power rule, I'm going to need to bring down the exponent, but unlike the first example here, we actually have coefficients on these. So we're going to combine the power rule with our third rule here, which is the constant multiple rule. Now again, what that constant multiple rule says is that whatever my coefficient is, goes along for the ride and is going to get multiplied to whatever the derivative of my function is. So in this case, the 3 is going to still be there. It's going to go along for the ride. And now I need to ultimately differentiate the x to the 5th. Using the power rule, the 5 can come down. I then get x to the 5 minus 1 power, which would give me 5x to the 4th. Now in our next step, we can go ahead and simplify and multiply the 3 times 5 to get us a coefficient of 15. But let's do the other terms first. Likewise, in the next term, the negative 7 there is a coefficient. It's going to go along for the ride. Using the power rule on x cubed, we're going to bring down the exponent of 3, and then we're going to get x to now the 3 minus first power, which would give us x squared. Now for our last function here, I secretly have a coefficient of 1. So although it just says plus x, we have that invisible 1 in front of it. Using the power rule, I still have the same idea. So that 1 is going to go along for the ride. I'm going to bring down the exponent, which is also a 1. And then I'm going to end up with x to the 1 minus first power, which would give me x to the 0. Now each one of these we can do a little bit of simplification with. So this is equal to the prior line. This simplified step is still f prime of x. I can multiply my coefficients here and get 15x to the 4th minus multiply again my coefficients to give me 21x squared. And then for this piece, my 1 times 1 would just give me plus 1. And another algebra skill that we might remember from properties of exponents would be anytime I've got a number to the 0 power, that would actually be equal to 1. So 1 times 1 would still just give me 1 as well. So anytime we see this x to the 1st, what's ultimately going to happen is I'm dropping down a power, so my x to the 1st is going to drop down to be a constant term, and I'm just going to get the coefficient in front of that. Okay, let's look at our third example. So here we have y equals 8 times x to the 10th minus e to the 3rd. We want to find the derivative by differentiating. I could use the operator or the prime notation. I'll use the prime notation again on this one. So I'm now finding y prime, which is the derivative of y. For this first piece here, we're going to use both the constant multiple rule and the power rule. So the 8's going to go along for the ride. We can use the power rule by bringing down the 10, and then we'll get x to now the 10 minus 1, or x to the 9th power. That will end up getting simplified, and we'll get 80 times x to the 9th for the first term. Now for our second term here, I have an exponent, but I've got to be careful. My base here is e, and e is Euler's number. It's approximately 2.7 and change. And so if I take a number and I cube it, I have that number times itself, which would ultimately still be a number. And anytime I differentiate a number, that derivative is going to be 0. Because those numbers as functions are just horizontal lines, and the slope of a horizontal line is 0. So it's really tempting to want to use the power rule, but I can't because my base here is not a variable like it was with the x to the 10th, but the base here is actually a number itself. And a number to a power is still a number. So derivative of e cubed will give us 0. And then we end up with just 80x to the 9th, and that would be our derivative. Okay, let's look at example 4. Here, we're going to start to see a fraction. So my original function here is h of x equals 1 over x to the 9th plus 20x. Now we talked about this at the start, but I cannot use the power rule from the denominator. So the first step I actually need to do is I need to rewrite this. So here I'm still having h of x. I'm not taking a derivative yet, but I'm algebraically going to rewrite this so that I can see every piece as x to a power. For the 1 over x to the 9th, we can rewrite that as x in the numerator, but the exponent will now become negative 9. And then plus 20x is already in the numerator, so we can leave that piece alone. Now from here, we can find our derivative. So I'm now finding h prime of x, my derivative of h. And for each of these, I can ultimately use the power rule. So our exponent comes down. We're going to get negative 9 x to now the negative 9 minus the first power. So remember, I'm subtracting off 1 in the exponent, which means if I have a negative exponent, it's going to become more negative. So I'm going to get x to the negative 10th. Then plus, for the 20x, that 20 as a scalar or as a coefficient is going to go along for the ride. X to the first, when I differentiate that, the 1 will come down and I'll get x to the 0, but x to the 0 would just give us 1. So our derivative here would give us negative 9 x to the negative 10th plus 20. Now, depending on the problem, it might ask us to simplify this a little bit, or if we have a multiple choice problem, we've got to make sure that we're finding an answer that matches one of the options. So another way to write our derivative would actually be to rewrite the x to the negative 10th back in the denominator as a positive exponent. Now, when we do this, the negative 9 stays in the numerator because the negative 9 does not have a negative exponent, and then the x to the 10th drops down to the denominator, and then we still have the plus 20. Both of those are equivalent answers, and depending on how we want it written, or maybe if it's a multiple choice question, which one was an option, we should be able to identify both of those. Okay, let's look at example 5. Why don't you guys try this one on your own first, and we'll check it together. So on example 5 here, I've got pi minus 3x to the 11th plus 4 over x squared, or x to the 7th. So here I can use the power rule on the first couple, but then on this last term, I'm going to first need to rewrite it. So again, this is still my original function y, which is why I'm putting equals to our original expression. So I've got pi minus 3x to the 11th, and plus I can rewrite 4 over x to the 7th as 4, which is still in the numerator, times x to now the negative 7th. From here, we're ready to go ahead and use our product or our power rule to find our derivative. I'm going to use the operator notation of dy over dx this time just to get a little variety in our notation. Pi itself is a constant because it's just a number. It's about 3.14. And if I take the derivative of any constant, what do we always get? Derivative of any constant would ultimately give us 0. So derivative of pi would be 0. With the negative 3x to the 11th, we can use the power rule for that. The coefficient's going to go along for the ride, so the negative 3 will still be there. Now the 11 will come down, and then we're going to get x to now the 11 minus 1, or x to the 10th power. And then plus, the 4 is going to still be there as a scalar. Derivative of x to the negative 7th would give us negative 7 x to the negative 8th, because again, we're subtracting 1. We can do a little bit of simplification here. Negative 3 times 11 would give us negative 33 x to the 10th, then we'll get negative 28x to the negative 8th. And again, if we want to rewrite that, if we're asked to do it all with positive exponents, we could rewrite this as 33x to the 10th, or negative 33x to the 10th, minus 28 all over x to the 8th by flipping down that exponent to make it positive. Okay, let's look at example 6 now. Here we have g of x is 6x to the 3 halves minus 2 over x plus 5x. Now the last two terms are similar to things we've seen. This first term is a little different. We now have a fractional exponent. Well, if you look back at the first page, we can use the power rule for any rational number, so this also works on fractions as well. Before we dive right in and do that, the first thing we want to do is rewrite though that 2 to the x so that x comes up to the numerator. So I still have 6 times x to the 3 halves. We can rewrite 2 over x as minus 2x to the negative first, plus the 5x. Now from here, let's go ahead and take a derivative. So let's find g prime of x. Same idea still applies. The 6 goes along for the ride. The 3 halves power will come down as our coefficient, and now I'm going to get x to the 3 halves power minus 1. So on the side over here, think about what has to be true in order to add or subtract fractions. Ultimately, we're going to need a common denominator, and I can rewrite 1 as 2 over 2, and 3 minus 2 would give us 1 all over 2. So we end up with x to the 1 half. For our next term, that negative 1 is going to come down. I'm going to go ahead and multiply those directly right away. So negative 2 times negative 1 would give us positive 2. Then we're going to get x to the negative second, and the derivative of 5x would give us just plus 5, since the x would end up being x to the 0 when we power rule. Oops, there is not a parenthesis at the end of it. I should have closed the parentheses right after the x to the 1 half. On our next step, let's start simplifying this. So 6 times 3 halves would ultimately give us 9. Then I've got x to the 1 half plus 2 times x to the negative second plus 5. Now, we've got a few things that we can actually simplify out with this. The x to the 1 half can be written differently as well. Anybody remember what x to the 1 half? Think about another way to rewrite that. Well, x to the 1/2 can actually be written as the square root of x, and potentially maybe the option on a multiple choice would be 9 times the square root of x. And then for our next term, we could rewrite that as 2 over x squared, and then plus 5 with that. That would be another way to write our final answer. Okay, let's look at example 7. So here in example 7, we have 5 times the square root of x plus 8 times x to the negative third. Now, 8x to the negative third is already ready to go. I can see the exponent in the numerator. It's a negative number, so I can use the power rule. But for the square root, I first need to rewrite that. Well, as we saw in our last problem, the square root of x is the same thing as x to the 1/2 power. So I'm going to go ahead and first rewrite the original function as 5x to the 1/2 plus the second term. Now from here, let's find our derivative. I'll call it dy over dx again. Again, you could also call that y prime if you prefer. Or depending on what the question's asking specifically, if it uses, and the question maybe says find y prime, I want to use that notation. Or if the question says find dy over dx, I want to be using that notation then. But in this case, I was just asked to differentiate, so I get to choose what notation I want to use. Now with the fractional exponent, same idea, power rule still applies. When we bring down the 1/2, we end up getting 5 times the 1/2, which will give us 5 halves. And then we get x. Now we've got the 1/2 minus first power, which will ultimately be 1/2 minus 2 over 2, which would give us negative 1/2. So our new exponent here will be x to the negative 1/2. Now the negative 3 will come down. I'm going to multiply that directly to the 8. So 8 times negative 3 is going to give us negative 24. And then we'll get x to the negative 4th by subtracting off 1. Again, I'm sorry, you should have closed your parentheses after the x to negative 1/2. Now, if we start simplifying this, we'd get 5 halves. Now, x to the negative 1/2 itself can actually flip down and become 1 over x to the positive 1/2. And then we get negative 24 over x to the 4th by making that a positive exponent as well. One other way to rewrite this would be to just kind of combine this as one fraction and then rewrite x to the 1/2 as the square root of x. So we get 5 over 2 times the square root of x minus 24 all over x to the 4th. Okay, let's do our last example here. Why don't you guys try example 8 on your own, and then we'll check it together. So with example 8, we've got 10x to the 12th minus 12 times the cube root of x minus pi to the 9th. So with that cube root, the first thing I want to do is rewrite that so I can see the fractional exponent. So 10x to the 12th is already good. We'll get minus 12. Now the cube root of x is x to the 1/3. So another kind of side note here to remember is that if I have the nth root of x, that would be x to the 1 over nth power. So the square root, our index there was a 2, which is why we got x to the 1/2. For a cube root, our index is a 3, so we'll get x to the 1/3. If I have, let's say, a 10th root of x, I'd get x to the 1/10. And that works for any index there. And we still have minus pi to the 9th. Now we can differentiate this by using the power rule. So our derivative here would be k prime. So again, I'm labeling the new function that I'm finding. When I bring down the 12, 10 times 12 would give us 120. And I'd end up with x to now the 11th by subtracting 1 off, minus 12 times that 1/3 that will come down. And then we'll get x to now the 1/3 minus 1, which would give us 1/3 minus 3/3, ultimately negative 2/3. And then for the pi to the 9th, the pi again, remember, is a number. If I take a number and I raise it to a power, I still have a number there. So the whole pi to the 9th is a constant, and the derivative of any constant is ultimately 0. Last thing I want to do is just kind of rewrite that negative exponent. So we still have 120x to the 11th. 12 times 1/3 would give us minus 4. X to the negative 2/3 could become 1 over x to the positive 2/3. And then minus 0 won't change anything. We could also rewrite that whole second term as one whole fraction with 4 over x to the 2/3. And if we were to do a little bit more simplification, rewrite x to the 2/3, 120, there we go. The 2 would be the exponent on it, so that would be x squared, and then that over 3 would actually be a cube root. So I could rewrite this as the cube root of x squared, or I could also do the cube root of x and then square that whole thing as well. And those are our first kind of 8 examples dealing with the power rule. So again, we've got all 4 of those rules that we were using at the top. The derivative of a constant is always 0, because the slope of a horizontal line would always be 0. And again, that derivative, always keep that in the back of your mind, is the slope of the tangent line, which is why we're looking at slope. The power rule works for any rational number as an exponent, so fractions, integers, negative numbers. And I bring down that power, so the n becomes my coefficient, and then I get x to the n minus first power, so I'm subtracting 1 off of my exponent. When I have a coefficient or a scalar in front, I can take the derivative of the function and just multiply by that scalar. And as we saw in all of these examples, if I add or subtract different terms together, then I can term by term differentiate. Other things we're going to have to start thinking about in future lessons is what happens if I multiply 2 functions? How would we deal with that? And what happens if I divide 2 functions? How would we deal with taking the derivatives of a product? And how would we deal with taking the derivatives of a quotient of 2 functions? And unfortunately, it's not as direct as the addition or the subtraction, so we're going to have coming up next what we call the product rule and the quotient rule.